Hi, welcome to me313 Mechanical Engineering Thermodynamics. The topic of this video is gas liquefaction, and the section in the textbook is 11.8. So here are the three learning outcomes. At the end of this, you'll understand how a gas can be liquefied through what's called the Linde-Hampson process. You'll be able to sketch the primary steps of this process on a TS diagram relative to the saturation curve, and you'll understand how this process can be solved for using an EES script. So first I want to describe the Linde-Hampson process. And the Linde-Hampson process is a liquefaction process. And the key is we're trying to liquefy a gas. Something maybe methane is a real common one, natural gas. But also we look at liquid nitrogen, liquid oxygen, even things like liquid helium and liquid hydrogen. And the problem with liquefying these things, a complicating thing, is that refrigerants aren't cold enough. Typical refrigerants are not cold enough to go ahead and reduce the temperature down to the liquefaction temperature, Tsat. So what we do is we have to do several processes, and then we eventually throttle it. So here's the primary steps of the Linde-Hampson process. We have a compressor followed by a heat exchanger, and this is actually a multi-stage compressor followed by heat exchanger. So what we'll do is we'll raise the pressure, and then we'll drop the temperature somewhat, raise the pressure, drop the temperature somewhat, and we do that until we end up to a fairly high pressure. And it's a fairly warm, but we've been able to reduce the temperature somewhat with these heat exchangers. We then run it through something called the regenerator, and we'll see where this comes in a little bit later in the process. But essentially, it gets cooled off by a cold liquid coming, or a cold vapor coming in this direction. Liquid's coming in that direction, and it loses heat into that. After it goes through the regenerator, it gets throttled, like a typical refrigerant, into a flash tank. And then in the flash tank, we go ahead and remove some of the liquid, and we'll call that fraction Y. Then this flash tank, the vapor comes up here, and this vapor is cold, and that's why it's able to cool off this incoming material in the regenerator. And then it comes back up to the process after it's warmed up very much, and then it gets recycled through here, and then we're going to have a makeup gas that's going to be coming in at point 1, and it's going to have the fraction Y that we removed in the liquid, so that this is a closed cycle. So I think to help explain this, it's good to see the whole process on a TS diagram. And here, I'm not going to redraw it. I'll use the one that's in the textbook, and it's sort of helpful here. So let's go back to all those steps and look at them on the TS diagram. As I said, going up from 2 to 3 was a multi-stage compressor with heat exchanger process. And so what we would do is we would go ahead and start at point 2. We would compress it and then cool it down, compress it, cool it down, compress it, cool it down, compress it. Now notice we're not able to drop the temperature all the way back down to the initial temperature. Usually you're using a conventional refrigerant, and you may drop it 30, 50 degrees each time in each one of these steps. And it may not be the exact same each time. We're slowly moving from what over here would be our lowest pressure up to our highest pressure, P high, and we're doing it in a sequence of steps. After we've run through that, we do our last cooling up to point 4, and that's as similar as each one of these steps right here. And then we're running through the regenerator, and the regenerator is 4 to 5, and it's being cooled from 8 to 9. So here's where the heat is going. The heat is going from that direction over here. So similar to regenerators we've seen in other cycles, in that direction. And what this does is it gets it cold enough, we go around the critical point over here. So at this point, we can go ahead and run it through the throttling valve, an isenthalpic throttling valve, drop it down here into the 2-phase region. And then we have our separator where we're taking the liquid out on that side, and then this is the vapor that we're going to recycle through it. This is the product. This is what we desire. And so how far this is the fraction Y that we're going to go ahead. I'm sorry, this is the fraction 1 minus Y that we want. And so we want this as far to the left as possible so we can go ahead and generate a lot of product. We'll find that the processes tend to be pretty far to the right, and you have a whole lot of material through the cycle. Now this vapor is also pretty cold. In fact, it's the same temperature. It's at this lowest temperature TL, and so that's why we're able to run it through the regenerator and pull this liquid, or actually it's a supercritical fluid, down around the critical point. And here's point 1. That's the makeup, and it's getting mixed with 9, and then we start again at point 2. Okay? So this is what's useful is that we're running refrigerants. Notice that are at temperatures in this range right up here. So this is the temperatures of a refrigerant. We're generating a liquid that is at a much, much lower temperature. It's Tsat at this pressure down here, which is usually around atmospheric, 100 kPa. is going to be much, much lower than the temperature of any of our refrigerants. And so that's where this usefulness and novelty of this process comes in. So what I want to do now is go ahead and solve this in EES. And I actually already have an existing script that does this. But I want to, before we go into that, I want to describe all the equations you're going to see in this EES script. And you've seen all these equations in thermodynamics. We're kind of putting together a lot of what you've learned over the last semester and the semester in the third. Right? So here I have the Linde-Hampson process, and we'll look at each one of these components individually in the equations. Now first we have is a multi-stage compressor. And so you might remember the intermediate pressure that we go to is this sort of this nth root of the low and the high pressure. So the one you may remember was we said if we had a single intercooler, P sub x was equal to the square root of P low and P high. Well, now we're looking at a more general where we've actually got maybe 3, 4, 5 stages of compression going between P low, P high. So we're taking the nth root, and then P sub I is the intermediate pressure. So I will go from 1 to n. And this will go ahead and give us a listing of the different pressures that we're going to at each one of these steps. This equation right here minimizes the compressor work, and that's where that equation comes from. You can go back to Chapter 7 and review that if you want on compression with intercooling. Right now, the work that goes into each individual compression step, because we'd like to know how much energy is going into here, is this equation right here. This is assuming an isentropic compressor, so this is going to be the minimum amount of work, and this is for each stage, so Pi over Pi sub 1. So what we're going to end up having to do is sum all of those to get the total work requirement for the entire process. And then, lastly, we would like to know what our temperatures are. As I said, this does not come back down to the starting temperature each time. It kind of ratchets up. And so we could go ahead and have this isentropic relation for the temperature, and then we're going to subtract however much is coming out of this intercooler. So we're going to define some delta T in here that will be a fixed value, and it's going to be kind of depend on what refrigerant that we were using. And usually the processes will define this as 30 degrees or 50 degrees, or how much we can bring it down each time. So those are the 3 equations that are going to describe these processes up here. 2 to 3 is actually several steps, as we see. So get some of the other equations. Down here is our regenerator, and so we're looking at H4 minus H5. We're doing an energy balance of the material going through here, and then what's coming up that is cold, actually we removed a fraction y on the bottom, so we weight it by 1 minus 5, and my H9 over H8. So there's my energy balance over the regenerator for that. Here's the energy balance for the throttling valve. It's pretty simple. It just says H5 is H6. We've seen that in the refrigerant before. And then lastly, in our flash tank down here in our separator, H6 is what's coming in. We're taking a fraction of liquid off at H7, and then the vapor is coming in at H8. And we know that H7, the quality of that is going to be 0, and H8, the quality of this is going to be equal to 1. So this right over here would be H sub F, and this would be H sub G at whatever the pressure is of this tank. And this is usually something pretty close to atmospheric. I'm back through the regenerator. And the last equation is we have a recombination right over here. We've got a mixing chamber. This is our makeup gas coming in. This is the recycled, and then it's going to go right back through the cycle. So here's the energy balance for that. Y of H1, because that's the makeup gas, 1 minus Y of H9. We subtracted a fraction Y, and that equals H2, and that's going to wrap it up. So we've got a whole bunch of equations that are going to appear in this script, but we can go ahead and have EES solve it for us, and that makes it pretty convenient. A lot better than doing it by hand. So let's go ahead and look at the EES script that does that. Okay, so here's the script. I'm going to go ahead and describe kind of the major components on it, and then you can go ahead and look at this in detail. So first of all, up here on the top, I defined this DT. This is just going to be the intercooler temperature drop for each one of the steps in the multi-stage compression. As I said, there's nothing that says we can drop it back down to the initial temperature, which you might want ideally, but usually you have some 30 or 50 degree change. So that's just defined in here. P sub 0 is going to be my inlet pressure, so I'm going to bet it atmospheric. And I'm going to have my system function such that I'm taking 5% of the liquid off, so I'm defining Y at 0.05. Now I've got some values for K and values for R for methane. So we're going to look at liquefaction of methane gas. We'll have our highest pressure at 5,000 kPa or 5 megapascals. And then this is kind of a neat thing we can do with EES, is I can go and define the number of compressors as a variable that maybe I can change later. So I'm going to say I have 5 stages of compression. And then these 3 equations, the pressure, work, and temperature equation of 3 you saw on the previous slide, to go ahead and give me what those pressures and temperatures are. So what you realize now is the number of steps that I have inside this whole process is going to be a function of what I enter and input in. And then I just find the enthalpy because I need all the enthalpies in the end. I sum up my networks. That's what W net is. Here's the intercooler that comes after the last stage of the compression. At this point, I'm just going to go ahead and set that equal to 0 since I don't have an intercooler, which we don't need, and we may look at that a little bit later. So here's some other energy balances. Our throttling valve, we equate the enthalpies. And notice now that all these states are going to be functions of n. Here's my separator equation, where I went on. This is also called the flash tank. And then here's my heat exchanger, also called the regenerator equation. So again, you can verify those equations with what you saw on the previous slide. And then here we're mixing back in when we're doing our makeup gas. Okay, the last thing here at the end, I just want to eventually look at this on a TS diagram. So what I've done here is just went ahead and calculated all my temperatures and entropies so we can go ahead and look at that. So let's go ahead and solve this. And EES actually solves this fairly quickly. And so let's go ahead and just look at our array table first and look at some of these values. So here you can see the pressure. Started in an atmospheric pressure, slowly ratcheted itself up to the 5 megapascals. Each time it was calculating the ideal intermediate pressure based on the number of stages that I had. You can see 1, 2, 3, 4, 5, the stages of compression I had. You can see the temperature. We started off at 145 after we mixed the makeup gas with the vapor that came out of the separator. And each time we compress it and cool it down 30 degrees, but it slowly ratchets itself up. But we can get refrigerants down in these temperatures. These are in Kelvin. We can get refrigerants that are in this sort of range. But what we can't get is tend to get them down here at around 100 Kelvin. Then our last stage is down here. We realize this 111, that's going to be what Tsat is. This is the temperature of my liquefied natural gas. All right. Let's look at just a couple other things we can look at in terms of our solution. Oops. Let's go ahead and look at our solution equation here. One of the things we can see here is our net work. So that's going to be in kilojoules per kilogram. So it tells me it takes about 2940 kilojoules to produce a kilogram of natural gas. And so that's just the compressor work so far. This isn't the temperature, the energy that would be required to be running the refrigerators. That would be an additional requirement we would need to know, and that would depend on the COP of all those particular refrigerators. But this is just the compressor work that we have. And then again, we defined n equals 5 for the number of stages that we have. But one of the interesting things, and this is another feature of EES I'm not sure I've shown before, is we can look at this on a property plot. So let's go ahead and do that. So we're going to go ahead and create, first we're going to create a property plot, and we're going to do this for methane. So I scroll down here until I find methane. And note, I don't want the word CH4. I want to use methane, so it's going to be a non-ideal gas. And then we can go ahead and plot some isobars on here. And what's interesting is, let's go ahead and put isobars for actually the pressures that are at my of each one of my compressors. So I'm going to type in those values that I have there. So, okay, so here I've created a property plot of methane, and I've drawn isobars for the pressures of all that were at each stage of my compressor. Now what I'm going to do is create an overlay with my solution. So I'm going to go ahead and create an overlay plot, and here I've got variables from my data from my array table, and so I'm going to create a TS diagram using those points on my solution. And I'll go ahead and adjust the color of that. And so here we go ahead and can see, if we zoom in a little bit, you can go ahead and see the process. So what's occurring up here in the upper right, these are our compressors. And remember, each time I compress up to the next pressure and then drop the temperature down, up to the next temperature, back down, up to the next temperature, back down, and I do that 5 times. Then right over here is my regenerator, so you can see that the energy from one side is going over to the energy on the other side. And then here I'm running through the throttling valve. I throttle down, and I'm only generating 5% liquid, so you realize this is going to be pretty far over to the right. So this is the liquid I'm grabbing on the left-hand side. Then this is the vapor that gets recycled back through. This is going, as you mentioned before, back through the regenerator. So this is kind of nice. You can see where all the different steps are on the diagram. This is actually pretty useful. You can do this with other EES problems as well.